The first talk we have for this afternoon is a topic that's near and dear to my heart, and it's covering reverse engineering of Apple's XProtect program and the signature. So round of applause for Koh.
Okay. Hello, everyone. I'm here to talk about reverse engineering XProtect Remediator. My name is Koh. I'm a cybersecurity researcher at a place called FFR Security, which is a Japanese security company. My current focus is on Apple product security, especially macOS. First off, I won't be able to cover everything in this 25-minute talk, but don't worry. I've just published a 71-page white paper that includes all the technical details. If you are interested in my research, please check it out. You can download it from the following link shown as a QR code. So I'm very grateful to Haruki and Phil Stokes for reading through my white paper and giving me insightful feedbacks. Okay, so I want to say this presentation is a deeply technical look at XProtect Remediator, or XPR. I will walk you through how XPR's remediation logic works, what kinds of malware are targeted by XPR. Just to be clear, this presentation does not cover the evaluation of XPR, so I won't be discussing how effective it is as a macOS security product. Also, I'm not gonna talk about a traditional XProtect, which is built in AV on macOS. If you are interested in that, I highly recommend checking out this just excellent talk. Here's an outline of this presentation. First, I'll give a background information to make sure we are on the same page, then move on to the tooling I use. After that, I will walk you through reversing results, and finally, we'll come to a conclusion. So what is XProtect Remediator in the first place? According to the Apple's platform security document, XProtect Remediator, or XPR, is a third layer of macOS malware defense. The first and second layers include App Store Review, Notarization, Gatekeeper, traditional XProtect. These two layers are designed to prevent malware from being distributed or executed. But XPR kicks in after malware has executed. Its job is to detect and remove malware that's actively running on the system. XPR was introduced in macOS Monterey as a replacement for MRT. Since then, MRT has stopped receiving updates. Now only XPR is updated typically once or twice a month. As of today, XPR contains more than 20 scanning modules. It's believed that each one targets a specific malware family. For example, a binary named XProtect Remediator, ADROAD, is a scanner that removes the well-known ADROAD adware. There's other XPR scanners like XProtect Remediator, Badcatcher, Bluetop, Bandroor, etc., etc. So why is remediation needed on macOS? It's because some malware bypass the first and second layers of defense. For example, in the 3CX supply chain attack reported 2 years ago, the Trojanized 3CX app was notarized by Apple, meaning that it passed Gatekeeper checks and launched successfully. Also, some malware uses social engineering to bypass the Gatekeeper. In both cases, malware can slip past the first and second layers of defense. So Apple needs a way to detect and remove such malware. But why do we care? From the defense security perspective, XPR is an interesting target for reversing. Since Apple tends to use its own naming scheme for malware, several malware families targeted by XPR still remain unknown. Researchers like Howard Oakley, Phil Stokes, Alden Schmidt have identified some of these, but several still remain unknown due to the lack of in-depth reversing. Also, XPR's remediation logic is too unclear. It seems to scan files using YARA root and delete any that matches, but is that all? That's still an open question. The main research target is this application bundle, XProtect app. Inside this bundle, under the contents macOS directory, there are more than 20 different scanning modules. They are all about 2 megabytes in size. There's a binary named XProtect, not to be confused with the traditional XProtect, there's an XPC service named XProtect Plugin Service. One notable thing is that these XPR-related binaries are written in Swift. As you can see on the slide, they have distinctive section names specific to Swift binaries, like, such as Swift5 entry, Swift5 typeref, etc. Okay, so next, let's move on to the tooling, how I did what I did. I analyzed more than 20 Swift binaries using Binary Ninja. Of course, these binaries are stripped, but surprisingly, some symbols can still be recovered. That's because I performed binary diffing and found that XPR scanners share functions with the libxprotect payloads dirlib. This means that we can import the symbols exported by the dirlib into the XPR scanners. That said, reversing XPR is still challenging because they are stripped Swift binaries. Swift binaries usually contain type-related symbols, things like type metadata accessor, protocol witness table, or PWTs. And these symbols are rarely helpful for reversing, since they tell us what kinds of objects are being instantiated. But in this case, these symbols are stripped as well, and so there's very little structural information left to work with. But fortunately, even if the binaries are stripped, we can still access a lot of type information in the binary. That's because Swift supports reflection. Metadata used for reflection can be accessed through Swift-specific sections, things like Swift5 protos, Swift5 types. By extracting this metadata, we can recover a lot of type information. We can extract this information using IPSW SwiftDump command, developed by Blacktop, but the extracted type metadata cannot be imported directly into a disassembler. So that's why I developed a plugin called Binja Swift Analyzer. I've just published it on GitHub. This plugin is based on IPSW SwiftDump command, and it annotates type metadata accessor, protocol witness table PWTs, and class method to the disassembly. I also support other features to help in Swift reversing, such as Swift string analysis. Here's a quick example. As we can see, before running the plugin, there's no type-related information available, so it's harder to tell what kinds of objects are being instantiated. But after running the plugin, a lot of type metadata gets annotated, so giving us lots of context information. I also developed a dynamic analysis tools to help in Swift reversing. Swift binaries contain lots of indirect branches, such as calls through vtable or PWTs, and resolving the branch targets manually using LLDB can be tedious. My LLDB script captures these branch targets and exports them as a JSON file. The exported data can be imported via my Binja plugin. Here's an example. The captured indirect branch targets can be imported into Binary Ninja like this. This plugin also annotates protocol witness table and the function symbol names when possible. For instance, when a function is called through PWT, this plugin annotates which protocol and which struct are associated with that call. So it provides plenty of useful information for reversing. Okay, next, let's move on to the reversing results. First, I will give an overview of how remediation works. Here's an overview. The contents macOS XProtect binary is registered as both launch agent and launch daemon. Its execution is scheduled by -CTS, which is a background task scheduler that runs processes based on the available resources and system activities. When the XProtect binary runs, it sends an XPC request to the XProtect plugin service, which then kicks off the XPR scanners one after another. Each scanner includes its own remediation logic, which is written using remediation builder DSL, along with something called XP plugin API. Also, I don't cover today's talk, but scanners also collect provenance extended attributes. while remediating threats. And finally, remediated threat information is reported back to Apple. Okay, then let's talk about how each XPR scanner is initialized. Each XPR scanner has a function model init func0, which runs before its entry point. Its role is to decrypt sensitive strings used for remediation, such as file path, regular expressions, YARA rules. These sensitive strings are encrypted using simple XOR cipher. Decrypting these strings is important because they tell us a lot about how each XPR scanner works. Auden from Huntress originally decrypted these strings. He also provided a nice binary ninja script for that. But some strings weren't successfully decrypted. So therefore, I developed a custom LLDB script that decrypts all these strings. Here are a few decryption results. We can see things like hashes, file paths, and text messages, and YARA rules, etc. Next, let's take a closer look at how XPR implements its remediation logic. Here, I'm going to introduce a set of domain-specific languages called Remediation Builder, which helps describe remediation logic in a clean and concise way. But before we get into detail, I'd like to start with my thoughts on why Apple decided to introduce this DSL. Why was it needed in the first place? Remediation logic can sometimes get complicated, and when it does, the code tends to become quite verbose. For example, let's say we want to delete a file only if the following conditions are met. The target file is located under library application support directory. Its file size is 2 megabytes or smaller. File format is macOS, not notarized. It matches a YARA rule. And if the scanner is running as root, an additional directory should also be scanned. If we implement it naively, it looks like this. This is an exaggerated example, but as we add more conditions, the nested if statements get deeper and deeper. This approach works, but it's not great in terms of readability and maintainability. If you want to add another condition, you have to insert yet another if statements, making the code even more cluttered. So how can we describe this logic more clearly and keeping maintainability? Apple's answer is to use Swift result builders. So what exactly are Swift result builders? They were introduced in Swift 5.4 to make it easier to write domain-specific language. If you've ever worked with SwiftUI, you've already used them. They are used to describe UI declaratively, but they are not just for UI. More generally, they can be used to create a DSL for collecting multiple elements and building a single result, like generating HTML, XML, JSON. In XPR, Apple uses result builder to combine multiple conditions into their final remediation decision. So what happens if we apply this idea to the remediation logic? Remember the example from earlier. By using a DSL provided by Swift result builders, we can express this much more cleanly. Here's what the same logic looks like. You can now easily understand what conditions are applied in this remediation logic, such as file size, file format, notarization status, etc. So this is exactly what Apple did. XPR comes with a set of domain-specific languages called Remediation Builder. It defines several elements, and each one provides a DSL for combining the remediation conditions. For instance, if we want to describe logic for a file-related remediation, we can use the DSL provided by File Remediation Builder. Other DSLs are also available, such as Process Remediation Builder, Service Remediation Builder, and Safari App Extension Remediation Builder. I've documented the Remediation Builder DSL specification based on my reversing. I've published it on GitHub repository. If you are interested in the details, such as how the DSL works and what kinds of conditions are available, feel free to check it out. Now let me show you one example to illustrate how this DSL is used in practice. Let's take a look at the Acre scanner. This is a simple example that uses file remediation builder. As you can see on the slide, a file is removed only if the path is temp acre, its file size is 68 bytes or more, and it matches a specific YARA rule. Yeah, it's pretty easy to understand. All right, so let's take a closer look at the remediation logic of other XPR scanners. Let's start with the load flight scanner, which was introduced at the same time as the rank stack scanner. Rank stack scanner is designed to remove the payloads using the 3.6 supply chain attack. As for load flight scanner, its decrypted strings are just 2 hash values. And what are these useful? Here's the remediation logic described using remediation builder DSL. As we can see, these 2 hash values are CD hashes. And this scanner is designed to kill the processes with those specific CD hashes. The first CD hash is a known one. This is a second stage payload using the 3.6 supply chain attack, commonly referred to as update agent. This sample was analyzed by Patrick Waldo and presented at Black Hat USA 2 years ago. The second CD hash remains unknown, but it's likely a variant of update agent. As far as I know, only one version of update agent has been publicly documented. This known version has limited capabilities. It only sends system information to the C2 server and doesn't perform any further actions. So Patrick Waldo suggested that there might be other more functional variants. This unknown CD hash could support his hypothesis that other more capable version of update agent might exist. Next up is a bad gadget scanner. Its decrypted strings do not seem to relate it to remediation, such as right-click, option-click, and click-open. So what are these useful? As it turns out, it's related to the malware I mentioned at the beginning of this talk. At the beginning, I briefly mentioned that the malware that uses social engineering to bypass Gatekeeper. The background image of the disk contains strings like right-click and click open. So that's exactly what the bad gadget scanner is detecting, strings in the background images of the disk. The bad gadget scanner enumerates mounted disks. Then it gets their background images and retrieves their text messages using OCR. After that, it searches for Gatekeeper bypass related strings, such as right-click, option-click, click open. If it finds such strings, it reports them to Apple. So which malware family does the bad gadget scanner detect? Honestly, I don't think it's aimed at any specific one. In fact, bad gadget scanner can detect disk images used by multiple malware families, such as Empire Transfer and Chrome Loader, Amos. So Apple may have designed bad gadget scanner as a threat hunting scanner to help identify new and emerging threats. Lastly, let's talk about the red pine scanner, which I think is the most interesting scanner. Although it's now retired, it offers some unique insights. Its decrypted strings are YARA rule and 4.5 path. Interestingly, the YARA rule detects a TriangleDB iOS implant. The TriangleDB is a piece of malware using the operation triangulation, a highly sophisticated attack reported 2 years ago. Researchers at Kaspersky analyzed this attack and suggested that macOS version of this implant might also exist. The macOS implant hasn't been publicly documented, but it's likely that red pine scanner was designed to detect that implant. Red-bind scanner is granted the entitlement COM-Apple system task port read, which allows it to read arbitrary process memory. It runs two separate scans. One scans the memory of running processes, and the other scans the loaded library path. The latter is called loaded library scanner. The first scan checks whether a memory executable matches the specific YARA rule. In this scan, platform processes are excluded from the scan targets. Why does red-bind scanner scan memory directly instead of the on-disk backing file? Normally, other XPR scanners perform their scans on the on-disk backing file. My hypothesis is that macOS implant runs entirely in memory, leaving no traces on disk. So to catch it, scanning memory directory is necessary. That would make sense considering the iOS implant was deployed entirely in memory. Next, let's take a closer look at the loaded library scanner. Here's the remediation logic. It checks whether a process has a specific loaded libraries based on file path. In this case, 4 file paths are specified: FM Core Framework, Core Location, AV Foundation, and libsqr3 directive. Here, what really caught my attention was the paths themselves. Do these actually point to directive files? When I look at these paths, I notice something strange. Except for libsqr3 directive, the others don't point to real files. For example, core location and AV foundation are just symlinks. So the loaded library scanner should specify the resolved path. What's even more puzzling is that FM Core Framework is a directory. So unclearly, no legitimate process would load a directory as a directive. So what's going on here? There are a few possible explanations. One is that this is just a bug in XPR. Apple may have accidentally included the wrong path. Another possibility is that the macOS implant somehow bypassed SIP and SSV, but doing something like that would mess with the system, so macOS becomes unstable. It's pretty unlikely. So I'd like to propose a third hypothesis. The macOS implant used its own reflective loader, and the loaded library scanner was designed to detect that. Researchers at Kaspersky pointed out that iOS implant used a reflective loader, and it's likely macOS implant used it as well. But when a directive is loaded through reflective loader, the backing file is usually empty. This was pointed out by Patrick Waldo last year at OBTS, and it is one of the few ways to detect reflective loading. But here's a thought. What if the implant set an arbitrary path as a backing file to make it safer? So to test this, I implemented a new reflective loader based on Patrick's research. Using it, I was able to specify a directory as a backing file. Here's an example. As we can see the output of VM map, the directory path named FM Core Framework is shown as a backing file. So this suggests that macOS implant may have done something similar. It used a custom reflective loader that assigns a fake backing file to blending. But Phil Stokes commented on my hypothesis. He said that XPR bug explanation cannot be ruled out because Apple has made numerous dumb mistakes over the years. But there's still some mysteries. If it can't specify any path as a backing file, why choose a directory of symlinks? Wouldn't it be more natural to specify and use the library instead? Another puzzling thing is that the red-bind scanner never performed remediation. Even when it detects malware, it just reports it to Apple, nothing more. If it's not designed to remove threats, what's the actual purpose of deploying it? Unfortunately, the answers remain unclear. All my findings are available on GitHub repository. It contains reversing results of 15 XPR scanners, so I hope they help with your future research. So let's wrap up with a quick summary. In this talk, I've walked you through how to reverse engineer XPRs and discuss its internals. So I didn't have time to cover everything, such as provenance sandbox and vulnerability research of XPR. They are discussed in the white paper, so please check it out if you are interested. Let me close with a few key takeaways. XPR gives insight into the Apple's exclusive threat intelligence. Security researchers should keep an eye on newly added scanners in the future updates. XPR scanner detection results may help discover new threats, because some XPR scanners appear to be designed to hunt new threats. So here's a disclaimer. So my DMs are open on X, so if you have any questions, feel free to reach out to me through social media. Yeah, thank you very much.